What's going on, everybody? This is the follow-up video to my dipole moments video that I was talking about earlier. So we're going to be doing the net dipole moments. I'm going to say movements probably at some point. That's a mispronunciation of it. That's a common misnomer, or what's the word for it? Dang. Can't remember the specific word for it where someone mispronounces it. I don't think it's misnomer though. But we're going to do the dipole moments for these three molecules. So I'm going to get a marker. And the marker is going to be my final moment. Let me make sure this works. Okay, that'll work. Good. So I'm going to use that for my final actual dipole moment. But I want to actually figure out the individual dipole moments. And for that, I'm going to use my pen here. So we have to figure out the dipole moment of every single interaction between all of the pieces of each of these molecules. So we'll start with Cl and C. If we go and if you check that table that I had linked, you may want to have that pulled up, or if you have your one from last year, you can actually just look at that one. But looking at the table there, chlorine has a dipole moment of 3.0, and carbon has a dipole of 2.5. So I'm gonna go ahead and write that down. C equals 2.5, Cl equals 3.0. I guess I might as well get all these other pieces that I'm gonna need while I'm there real quick. H equals 2.1. Fluorine represents 4.0. And nitrogen equals 3.0. Okay, so we've got all the pieces that I'm going to need for this example here. So starting with this carbon-carbon bond. Carbon and carbon, they're the same thing. So there is no net dipole between these two carbons. This carbon and this chlorine, though, there's going to be 2.5 for carbon, 3.0 for chlorine. So there's going to be a slight pull towards this chlorine, and a slight pull towards this chlorine, a slight pull towards this chlorine, and a slight pull towards this chlorine. Now, because these angles are consistent and they're actually angled the exact same way apart, in these two, this process is going to be a simplified version of vector addition. But here we've got these two chlorines. This is going to be at the same angle upwards as this is downwards. So we can actually simplify these two as it's pulling away from the carbon this direction. Same thing here. This is going to be the same upward angle as this is the downward angle. So it's going to be pulling in this direction. And notice that these arrows are going to be pointing the exact opposite directions. And if we were to combine this arrow with this arrow, we would be left with no dipole. There is none. All of the dipoles cancel each other out. Okay, well, let's go to the next one, and it'll be a little bit different. So here we've got carbon. Carbon has 2.5, and then hydrogen has 2.1. Now, that's not that much of a difference, so we're going to actually represent that by a pretty small arrow. Now, I know this one was 0.5 apart, and this one's 0.4 apart, but it is actually a pretty big difference. So in this case, our carbon is slightly more likely to get each of these hydrogens. And remember, this would be a tetrahedral shape. This is not like they're in a three-pronged position. This one's actually like they're, if I get my model kit out, I think I should have it close by-ish. Okay. I'll actually build the first one too, just to kind of help explain that at the end of this. So let's go ahead and these are another type of problem where building it in the actual model kit may actually be helpful for you. Let's go ahead and get this bad boy built as well. Okay, just to go back to that first one really quick. So if you see when you actually build it, they're angled the exact same way apart from each other. So these guys are going to cancel each other out with their up and their down angles. Same thing over here. And then because they're exactly symmetrical, they're going to kind of pull all their electrons in the exact same way away from this middle area. And that means that it's actually going to just completely cancel out. There will be negative charge, but it'll be all kind of around the edges here. There is no actual net dipole. The whole thing is just going to kind of be slightly negative. But looking at this one, all three of these hydrogens here are going to slightly funnel their electrons in towards this carbon. And then between the carbon and the chlorine, chlorine is, again, 3.0, and this is 2.5. So that arrow is going to point this direction. So if we were to take the net result of three arrows kind of pointing inwards like this, and then this one right here, our net dipole is going to look like this. It's going to move towards the chlorine there, because all three of these are going to kind of funnel upwards towards here. All three of these are going to funnel upwards towards here. The angles of all these will also kind of cancel each other out, and you'll be left with just an arrow pointing towards carbon, and then you'll have an arrow pointing from the carbon towards the chlorine. That's one straight line showing the dipole is going to point that direction. Then for the last one, let me get a nitrogen out here. And we're going to put on our fluorines. So this nitrogen right here, it doesn't have a dot because that's where a bunch of electrons are, and then there's three fluorines down here at the bottom. Nitrogen has a thing of 3.0, and then fluorine has 4.0. So all of these are going to get pulled down towards the fluorine. And again, just like with the hydrogens here, the angles that they're kind of positioned at mean that they're going to average together their vector sum of parts, which again, you don't need to really know what that means. If you take physics, you'll learn a lot more about what that's talking about. All of these are going to point this way. Even though they all have electrons around it, the fact that the fluorine is so much higher electronegative-wise means that the dipole is actually going to point this direction. So the last one we had, if I hold them kind of side by side, this one, it would have kind of been like arrow-shaped almost. It would have been kind of, the electrons would have bulbed this way and been a lot smaller down here. And then kind of the opposite thing is happening here. We've got all of this big area that's a really massive area generalized with a negative charge. And then you have this smaller area of slightly less negative charge. And again, we can represent these. This is not an actual positive charge or an actual negative charge. It's just slightly positive and slightly negative. So this one's going to be slightly more positive, and this side here is going to be slightly more negative. So that's how you would draw your net dipoles. I hope that makes sense. If you have any questions, let me know. There should be a worksheet related to all of this. You can work on that as well. Have a good rest of your day, everybody.